Let's do another optimization problem, but this time there's a demand function, so it's going to be a little trickier. So a concert promoter has found that if she sells tickets for $50 each, she can sell 1,200 tickets. But for every $5 she raises the price, approximately 50 less people attend. What price should she sell the tickets at to maximize her revenue? So, and this time I'm not going to go through the step-by-step process exactly, but I'm going to go through some similar logic, okay? If you want to very accurately check off each step, go ahead, you can follow this as a good guide, but let's just look at the problem. All right, so we can sell tickets for $50 each, right? 50 each. And then can sell 1,200 at this price. But if she raises the price, right, if she sells them for 55 each, she loses 50 people. So it could sell 1,150. Raise the price again, could sell only 1,100, etc. Okay, let's assume that there's a linear relationship here. It doesn't actually tell us to assume that. It should tell us to assume a linear relationship or a different relationship. It should tell us what they're looking for, but we'll just assume linear here. Okay, so what price should she sell in order to maximize the revenue? That's our objective function. We want to maximize the revenue. So what is revenue? Can't really draw a picture here that I can see, but we do need some variables. Well, there's a price that we charge for the tickets, and there's the quantity of tickets that we can sell. Just like we've been talking about for so long, well, not so long, I'm exaggerating, but it's a very common thing in our class that a lot of times our revenue is just going to be, what do you charge? How many do you sell? Multiply them together. This is the function we want to maximize. What's our domain? Well, we have to sell. We can't charge $0 or negative dollars. And, we're not going to have negative people. I guess we could sell 0 tickets. 0 is included here, I guess. All right. There we go. That's our domain. These are the numbers that make sense. Kind of looks like a happy face here. You see it? Right? Yeah. Or it kind of looks like they're maybe crying with the P. I don't know. Okay, so this is our objective function. Right? Objective function. This is our domain. The inputs that make sense. Now we need the constraints. Because we have 2 variables. So we need to use a constraint equation to get rid of one of those variables. So this is the constraint here. There's no other real requirement here, but there's a relationship between the price. We can't just sell 50 tickets and sell 2,000 of them. Also, realistically, there should be a maximum here for Q, but we don't know it. It didn't tell us, how many tickets we can sell. Maybe we'll just be like airplanes and sell more tickets than we have seats for. I don't know. But yeah, here we go. What's the relationship here? That's a little harder. That's a little harder here to find the relationship here. But it's like a line. It's a linear relationship. Every price increase of 5, the tickets decrease by 50. So let's find the slope. It doesn't matter which one you solve for, but we have a line here. Y equals mx plus b. But our variables here are q and p. Right? So instead of writing y, you can write q or p. It doesn't matter which one. Instead of x, you can write p. This is a line. The only reason I chose this is because I wrote p on the left here and q on the right here. Usually we do that with x and y. But you could do either one. So what's the slope of this line and what's the y-intercept? How can we find that? Well, the slope, right? Slope is normally, I'm going to write this in red. Slope is normally, you know, the difference in the y's over the difference in the x's. We don't have y's and x's here though, right? We have q's and p's. So pick, I don't know, you can pick any pair. Look at these two right here. So the second one is 1150. The first quantity is 1200. The second price is 55. The first price is 50. We're going to get negative 50 over 5. Our slope is negative 10. Okay, so we know that, notice our constraint equation is kind of getting a little involved, a little difficult to find, but we're making progress. We know that our constraint equation, our line, our demand equation, the relationship between how much we can charge and how many people will buy the tickets, we now have the slope. The quantity of tickets we can sell is negative 10 times the price plus some B value. We need to solve for B. So we just plug in a price, plug in a quantity. Choose any one you want. I'm going to choose this one so I don't have to scroll. It'll all give you the same number. We can sell 1,100 tickets at a price of $60. Let's find what B has to be. So 1,100 is negative 600 plus B. Okay, B is 1,700. Whew. We now finally have our constraint. We have our demand function. We know that the number of tickets we can sell is negative 10 times the price that we charge plus 1,700. So if we didn't sell any, or sorry, if we didn't charge anything, if we just gave these tickets out for free, this model says we would give them to 1,700 people. And at any other price, we can check our answer, right? If we charge $50, this becomes negative 500. This becomes 1,200. Good. At a price of $50, we should have been able to sell 1,200. So this constraint equation looks pretty good. The next step was solving our constraint equation for one variable so we can substitute it into the objective function. Well, I've got good news for everyone. Our constraint equation is already solved for one variable. So we can just plug it in directly. Let's plug it in to our objective function. And now we get revenue as a single function of P is P times Q, and Q is negative 10P plus 1,700. We've already done very similar things in this class as to what we're doing right now. And again, most of the difficulty in this question is this blue box over here. That's not calculus at all. That's algebra. The algebra and the setting up of the problem. We haven't even started the calculus yet. The calculus is going to be the easy part of this section. And again, our domain is that P has to be positive. Oh, I wrote off the edge of your screen. P has to be positive as our domain. And Q has to be positive. When is Q positive here? That's a little bit more involved of a question. But notice if P is 1,000, well, October raced through the house so fast that she clotheslined herself on my cable and broke the actual connector. Anyway, let's continue. All right, so we could find what quantity it has to be. For example, if the price is $170, then you can see that nobody will buy it. So that's the maximum price. But I don't think I'm going to make you guys do that. So let's move on. We need to find now the global extremum of this function. Let's simplify it a little bit first. Okay. When we distribute the p, we get negative 10 p squared plus 1700 p. All right. So what do we know about this parabola? First off, we know that it's a parabola, right? This is a quadratic function, and it opens down because this is negative. So we know that a quadratic function is going to have a maximum at the vertex. And so in the past, we used a vertex formula to find where the vertex happened. Now let's find the vertex with calculus, because we know that vertex will be the global maximum. And we want to maximize the revenue. But the global max will be at the vertex. So r prime of p is its derivative, which is negative 20p plus 1700. We need to find the global maximum. That's at the vertex. That's going to be a critical point. R prime of p equals 0 when 0 equals negative 20p plus 1700. That's when 20p equals 1700, or p is 85. Let's find out. 1700 divided by whatever that other thing was 85. Great. So we should really knock the price up. $50 per ticket? No way. $85 per ticket is way to go. All right. So that's all the question asked us to find. You should charge $85 per ticket. And this is sufficient. This is good enough. But really, the best answer does incorporate more information. This sells. Let's find out how many tickets that sells. Okay. Let's look at our demand equation. If P is 85, right, then Q is negative 10 times P plus 1700. So Q will be also 850, I believe. All right, negative 850 plus 1700 is also 850. So this sells 850 tickets for a revenue. I did not spell tickets right. Tickets. Revenue of 85 times 850. $72,250. Great. This is the best answer. Answers the question and gives a little bit of context. Okay? Context. Let's see if our answer makes sense. Does it make sense that she could sell tickets for $85 each? Seems like a plausible number. We should be selling fewer than 1,200 tickets. Yeah, we are. Good, because we're charging more, so it's going to be less than 1,200. Revenue of $72,000 seems like a lot, but she's selling a lot of tickets at a big price, so sure. And of course, profit will be much smaller. There must be a ton of costs involved in all of this that we don't know of. But in terms of revenue, this is where the revenue is maximized. There it is. Let me know if you have any questions. Hopefully these problems are getting a little easier, but you can see that each problem is a little different. This problem, finding the demand equation in this big blue area, was the hardest part, I think. Everything else is pretty similar. We found the maximum a little differently than we did before because we made use of the fact that we knew this function was a parabola. That lets us do things a little bit in a different way, a little simpler. We didn't have to consider the endpoints because we know, right? I don't care where you go on either side, it's the parabola is going down. So you can use information of math to kind of make your lives easier when you can spot it. Or you could do the same analysis that we did in the previous problem. Let me know if you have any questions, and good luck.